A lot of people saying, oh, quantum computing is fake. You know, it's bullshit. It's going to be here in 30 years, if ever. And so there's a lot of like sort of quantum skeptics or quantum deniers, if I, you know.
They're quantum deniers?
Yeah, I know, if I use a pejorative term,
I didn't know that. Quantum computers there's immense advances. That might as well, even if you don't believe in it, how about you be prepared for it?
Welcome to the show, everybody. This is the Quantus podcast. We've got a very special surprise guest today. We've got Dr. Zina. Can you say your full name?
Dr. Zina Cinker.
Dr. Zina Cinker.
Yep.
And so welcome to Forest City, Malaysia. We're in this marina hotel. It's quite grand. And
I love it. This is so unexpected. I had no idea this was here. This is so cool.
Yeah, it's a little island, you know. I mean, it's a little bit of a bubble, and but yeah, I think you'll meet lots of great people here.
I already did.
Well, well, thanks for coming down. We met you at this quantum conference, and they just said, no, we have to get this person over here. So can you tell us a little bit about all the exciting stuff you're into? I know you've got the Expanse, and then Puzzle X, but you were a professor of condensed matter physics, something like that.
Yeah.
Okay, so all right, what's going on with?
I was at GITEX in Singapore, which is like this big event that happens, and then they've started something also in Singapore, and I was giving a talk which was about quantum and kind of how do we see the future with these exponential technologies, and quantum being one of them. And then I got the pleasure of talking with some of your colleagues and some of your folks, and they were telling me Malaysia is right here and we have this cool thing. Come, and here I am.
Okay.
So that was, I think, serendipity sometimes for these things is amazing. But I was talking about quantum. So my background is I'm a condensed matter physicist by background. So my world is atoms and molecules, not zeros and ones.
Okay, hold on. Let me just pause there. What is condensed matter? I mean, isn't all matter condensed at some level?
Ooh, good question. Actually, no. Condensed matter physics is the physics where you can predict what is going to be happening in a crystalline lattice. Like, I'll tell you what that means.
Okay.
Is that, you know, squishy things like biology, like cells, there's not a structure to it. But if I give you a silicon structure, if I give you a crystalline structure, if an atom is here, and next one is here, and next one is here, they all have the same properties.
It's very predictable.
Very predictable. That's the reason why we can create the things like our phones, because these are all based on condensed matter physics. The laws of this area and that area are exactly the same. So when we look at kind of how do we create these boundaries and boundary conditions for something like this, you don't study the whole thing. You only study this part, knowing that the same exact thing applies over there.
So it allows you to generalize effectively.
It does, and it allows us to create things like we are doing with silicon infrastructure, with all of the kind of magnificent things that we do in semiconductors. Everything is based on condensed matter physics. So that's kind of what I do. I don't understand squishy stuff like biology. This is like a different field, so condensed matter physics is here. Liquids, again, not condensed matter. They have very different complex behavior.
So it's solids, but not just any solid. It's actually highly regular. So basically it's
You're
crystals.
Right, absolutely.
You're a crystal scientist.
I am a crystal scientist. I mean, I'm a physicist. And my study was, my PhD and postdoc studies are on this material called graphene, which a lot of people know about because it won the Nobel Prize. And I'm a graphene scientist by background.
So that's like really thin wafers?
Yeah, you are.
Carbon?
You are absolutely right. It's one atomic layer of carbon. It is the thinnest and strongest material that we've ever known. And what I did for my research was that I would study what happens when an electron and a photon, which is a packet of light, would interact in graphene in a 1 million times a billionth of a second, a femtosecond. That's
a femtosecond. Wait, hold on. Just say that whole thing again. Wait, so you're predicting what in a femtosecond?
So the whole field is called, it's femtosecond ultrafast spectroscopy. So that is, my field is femtoseconds ultrafast spectroscopy dynamics in graphene. So that is.
Okay, so the idea, when I think of spectroscopy, I think of like you like shoot some light at something and then it bounces back.
You're absolutely right. That is what it is.
And then you get some info about the thing.
That is exactly what it is.
But in the case of graphene, you already know what it is.
No, We don't. I mean, nothing. We know nothing about anything. I mean, we know so little about anything around us, and there's always so much more to be discovered.
Okay. So the idea is that you already know it's graphene, but you're going to bounce some light off of it to learn more about it.
Absolutely. We're trying to understand when photons, which is light, interacts with the electrons in graphene, what happens in very, very early stages. So in the later stages, which is like picosecond, which is like 10 to the 12, which is like a million times or something later. That stuff is a lot more studied. We study what happens at that very, very early moments where when light hits it.
I mean, how is there? It almost sounds like it's so short that like light doesn't even have time to do anything. It just hits one part of it. Oh, it does? It does things?
It does. And then that's kind of a lot of people. People tell us, so what's the application for that? And the answer is there is no application for it. That is so true. Because there is a part of science, which I kind of belong to, which is fundamental science or basic science. We don't do things for application. It's not engineering. We don't do these things because we think that if we study this is going to happen.
Sure.
We study it for the sake of science.
I remember my professor, I studied math, and I remember asking, I was like, hey, what are the applications of this? And he said, well, first of all, you're not supposed to care. And second, you'll find out later. So, and I didn't find out later. I actually found that there are all these pre-existing, applications.
Well, I guess the good thing is that there were applications.
There were, yeah. So I mean, of course, sometimes it takes a long time for these applications to emerge, right? I mean,
Absolutely.
like how long was number theory around before people came up with the cryptography that uses
Yes.
it? So let's talk about graphene for a second, because this is a pretty deep topic. So I understand that, like, okay, so why is graphene strong? Because it seems like it should be weak. It's like paper thin. It's thinner than paper. There's nothing thinner than it. Why would it be strong? There is
a misconception that people think about. They think that, when we say graphene is 200 times stronger than steel, people think that it cannot be destroyed, but that's not the case. When we say 200 times stronger than steel, it's 200 times stronger than steel in its equivalent weight in steel, okay?
So if you had a kilogram of graphene and a kilogram of steel.
Yes,
okay.
That's the structure. But graphene is a truly two-dimensional material, meaning that the surface area compared to its thickness is so big.
It's basically two-dimensional.
It is two-dimensional. It's not just that it is two-dimensional because it's big. The laws of physics change in a two-dimensional. They have nowhere else to go. An electron going through a truly two-dimensional lattice doesn't have anywhere else to go. It only goes in this plane. And the laws of physics for it going through this plane is completely different than the crystalline structure that we have. Because when you think about it, a lot of our devices in the 3D structure that you have, you can go through this plane, but also it can scatter up and down, right?
There's more degrees of freedom.
Absolutely, and that's how a lot of these things that result in heating phenomena, etc. It's because of the scattering of these, what we call them phonons, which are the vibration of the crystalline structure. So graphene doesn't have that. These two-dimensional materials only have one plane.
Okay,
and that makes the physics of it super cool, and that's why it won the Nobel Prize, because it was just like, wow, we never thought that this thing would actually exist, and it does exist.
But how do you manufacture something that's one atom thick? I mean,
good question. We should ask, Kostya Novoselov, Sir Kostya Novoselov, who is a Nobel Prize winner in graphene, who won the Nobel Prize, and he was 35 when he died.
Wow.
Yes, he's actually on my advisory board. So
okay, all right, okay.
He's fascinating. It's amazing, and the story of how they got this was that they were having these Friday night cool experiment things where they would gather Friday night, they would have some beers, and then they would do some exploratory fun stuff, right? And they grab a piece of graphite. So graphite is, if you think about it, graphite is like millions and billions of layers of graphene stacked on top of each other.
Okay,
the reason why you can write with a pencil, with the lead of the pencil is graphite, is because every time you're writing, many of those layers come off.
Okay, but it's interesting that it's layered. I mean, because that sort of implies a certain, because it's not a sort of symmetric in all three dimensions. It's sort of like it's got a 2D symmetry, and then that's copy pasted.
It is. You can think of it as like stack of thousands of papers, right?
Okay.
So imagine if you got thousands of papers, like a stack, right? And if you had that and then you were kind of leaving some of that behind, these big chunks of these layers that were coming off, that is basically how we write with a pencil. So now the amazing thing is, can we just extract and isolate one of those layers?
Okay.
The whole field was created based on the ability to be able to isolate only one of them. And the way they did it is magnificent, because it wasn't like they were just having their fun, like weird science, cool nerds experiments, drinking beer probably, and doing all these things in the lab on Friday nights. And what they did was that they got, Scotch tape, right? The Scotch tape that we have. So they put a piece of graphite in Scotch tape and they kept peeling it off. So they'll put one, they'll peel it off. Okay, so a bunch of these layers would come off. Then they put that one, put it on another Scotch tape, they will peel it off. A bunch of other layers
Literally
would come
Scotch
off.
tape? Is this a
literally
metaphor?
Scotch.
Okay, all right.
It's not a metaphor, it is
Okay.
literally Scotch tape. Okay, we literally in the clean room, we still use Scotch tape method. And then they would, at some point when you can't see anything, right? But they would look at it under the microscope just
Okay.
for fun. Okay, it's like, oh, look at this. And they were able to find one layer of
Okay.
that. And because of the opacity distinction of it, they could tell that this is only one layer. That is the story of graphene. Out of a fun experiment on a Friday night of them using Scotch tape just for fun,
Wow.
they discovered this one atomic layer, and then the whole field started, and they won a Nobel Prize for it.
Wow. Well, okay, and how well does this technique generalize to say other things? Like, okay, is there like an analog of graphene for, I don't know, say oxygen or iron or like any of these other? Is it only carbon that does this?
No, good question, because the field started with graphene, and probably because it was the easiest, right? Graphite or carbon in this layer is already like these stacks of paper, right? Easy to say, okay, we can extract this two-dimensional layer. And for a very long time, for years, the field was dominated by graphene only. But since then, it's been 2 years. It was discovered in 2004. We have discovered hundreds of these two-dimensional materials. It's a whole field called two-dimensional material field.
Okay, wow.
Graphene is the passé one these days. A lot of people don't pay attention to
New
it.
kids on the block.
But yes, there are many of them. I mean, there's even like there are many scientists who work on things like goldine, so one atomic layer of gold, like
Wow.
silicene.
Also,
one
if you
atomic.
see ene on the end, that's
Yeah,
what that
a lot of
is.
them
Okay,
are like
ironine.
that. Brophene, like there are a lot of different classes of these materials. But when it gets really interesting, is that graphene is a semi-metal. So for those geeks and nerds who know physics, I mean, there is metals, and then there's semiconductors. You know what I mean? That there is a difference between them. In electrons in metals can go freely wherever they want, and that's why electrons flow. You have mobility within them. You have current flows through them, and semiconductors, like the ones that we have in our devices, are the reason why we can do zeros and ones, that we can turn them on and off, right? There is a band gap between these things. So if you think about it, like electrons in graphene can just, in a metal, they can just go straight. There is nothing opposing them. In semiconductors like silicon, the beauty of silicon is that silicon has a gap in its band diagram infrastructure, which means that the electrons cannot go through unless you create like a condition for them to be able to jump over. And that allows you to basically create the whole digital infrastructure. Zeros and ones is based on this thing that I can turn it on or off.
Right,
You
so
can't do that with metal.
Yeah, I mean, when you put it like this, in some sense, classical computers are already quantum. I mean, there's quantum effects inside of the computer.
The quantum effects are everywhere
Right.
around us. I mean, one of the most, people don't realize that, people think that quantum is this weird, eerie thing, or say quantum phenomena are around us, are basically the governing rules of the world of small is the quantum mechanics. So we tell people, don't think quantum is something specific we do in the lab. The rules that govern atoms and particles are called quantum mechanics.
So everything
is
is
it.
quantum, actually.
Everything is quantum.
Okay.
In the basis of what we do, everything is quantum. As a material scientist, the governing rules and laws that we use that allows us to, again, create all these electronics and everything are basically quantum mechanics. It's been around for 100 years, meaning the rules have been around from the beginning of time, but the infrastructure we've been able to create to understand them, quantum mechanics has been around for 100 years. This is a 101-year anniversary of quantum mechanics this year.
Oh, wow, okay.
Yes, last year was the 100-year anniversary of quantum, proclaimed by the United Nations as International Year of Quantum, which we were also involved in very strongly. But then one of the other phenomena in quantum that people don't know about, which is a room temperature quantum phenomena that happens is photosynthesis. Photosynthesis is one of the most common quantum phenomena that happens.
Wait, so plants are quantum?
In a certain sense, with the photosynthesis, the efficiency of photosynthesis that happens, there is no other way for it to happen besides it being quantum. So it's a quantum phenomenon that happens. It finds the best and most amazing pathway for it to kind of find its way. And we were talking about something again on the panel that I was yesterday. We're talking about quantum navigation and how they're using instead of GPS, they're using quantum navigation, et cetera, et cetera. And that's one of the things that is based on the navigation systems that birds use. They use quantum navigation. In birds.
Oh, really?
Yes.
Let's quickly bounce through your, you've got some organizations that are pretty interesting. Can you give me a rapid fire? Like, what are those?
I run a think tank. We have 20,000 members and 30 country chapters. We work mostly with governments. So governments on the strategy for exponential technologies. Quantum is not the only area that we work in. Prior to that, it was advanced materials. With the government of Spain, it was quantum. With now we're working with the Sovereign Fund of Abu Dhabi, ATQ, that hosted one of the events that we had called Expanse. And we help leaders, especially governments, municipalities, cities, to understand what happens in the wake of these exponential technologies when they're coming their way. How can they be prepared? What is going to happen for the next chapter for them? And we've got a lot of fun doing that.
And that's the name of that organization is?
Matter.
Matter. Okay.
Yes.
And then you also have Expanse?
Yes, so Matter, we do a lot of different initiatives. We work with the UN, all of those things, blah, 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 lots of different things. But a lot of people know us for our events. So what they would remember us for is Expanse, Puzzle X in Barcelona. I was there for 3 years with the City Hall of Barcelona. Expanse in Abu Dhabi. Prior to that, we were in the US. But that is the front-facing things that we do. On the back of it, we do a lot of policy, we do work with the UN, and a lot of things that are not necessarily that.
Understood. So I don't know how deep in blockchain you are.
Zero. That's the one thing we do not do is blockchain.
Okay, so the idea is we're trying to, make a form of money that doesn't require governments or banks to work. That all people of the earth could use, and it's quite ambitious and idealistic, and and a bit naive at times. But there's the latest hullabaloo is quantum computers, because basically all the blockchains, not all, but almost all the blockchains are pre-quantum. They're using elliptic curves, which are vulnerable to Shor's algorithm, which could run on a quantum computer in polynomial time. So it's basically all the cryptographic assumptions that we built all the blockchains on are no longer true in a world where we have quantum computers at scale.
Oh, okay.
So it's a hairy situation. Now, blockchains aren't the only ones with this situation. Most of the internet has run on elliptic curves or RSA for quite a while. But blockchains are sort of uniquely vulnerable in that it's difficult to upgrade them on average, and users control their own key material. So you can't just sort of press a button and force everybody to upgrade. Instead, you have to convince everybody to upgrade. And of course, now you're talking to users about cryptography, which they normally would never think about and have no idea what you're talking about. And so then another side of that is, so then you got a lot of people saying, oh, quantum computing is fake, or it's bullshit. It's going to be here in 30 years, if ever. And so there's a lot of sort of quantum skeptics or quantum deniers.
They're quantum deniers?
Yeah, I know. If I use a pejorative term,
I didn't know that.
and so, what would you say to the quantum deniers? I mean, I
didn't know you existed. Quantum deniers.
I know, they're basically like the flat earthers of the modern times. But not if I take it as if I take a steelman position of it. Basically, there's been many claims of quantum computing companies over the past decades that they were right around the corner from some big breakthrough, and it didn't materialize because you can't guarantee that this breakthrough is going to happen technologically. It's a sort of, it has its own schedule. But they would, as companies do, exaggerate or even maybe fabricate some of their results, and so people became skeptical, and I think that's a legitimate point of view.
That is legitimate, but I would tell these quantum deniers and everybody else the same thing we tell a lot of our decision makers and governments when we talk to them. The problem, they're right. You know what I mean? Sometimes we talk to governments and they say, you know what, one day in the news I read that you say, hey, you know what, quantum is 30 years away, and then tomorrow I see in the news that you guys are saying, hey, quantum is here and this is a commercial. They're right, but none of those things are contradicting each other. Quantum technologies is an umbrella term that is used for many class of technologies which are using quantum mechanics and quantum phenomena. And I just told you that quantum phenomena rules everything.
Sure. Sure, in some sense, so even the boundary of what is a quantum technology and what isn't is actually
I will
kind of
tell you,
fuzzy.
no, I mean, it's very simple. When we're talking about a lot, there are these three different classes of quantum technologies. The one that we're talking about is a quantum computing, which everybody's like, oh, it's so far away, et cetera, which is not that far away. But the other one that you hear to say, oh, it's here, quantum communication, for example. Quantum communication has nothing to do with quantum computing.
Okay.
Quantum communication is here. Quantum communication is being used. The ships, the Navy ships of China are right now quantum linked, okay? This is not quantum computers. Quantum communication is based on, you guys would appreciate that, is the quantum key distribution, which is when you send the key, if you think about it, there's this quantum phenomena that a particle observed knows it's being observed. You've heard it, right?
Sure.
It's so spooky, but it is a reality of the situation. So if you have a quantum link and you intercept it, you will know you've been intercepted. It is not based on it is quantum phenomena. You will know because the state of that it changes. So quantum communication is based on that phenomena. It is used. It's not something that we say, oh, it's far away. No, it's used.
Right, but so I guess the counterpoint to that would be like, yeah, okay, QKD is real, but that's easier to do than quantum computing.
It's just a different thing. It's apples and oranges, and then we have quantum sensing, and that is a completely different thing that is being used.
Something in the news just recently. The CIA leaked a secret. They had a marketing thing. They said that they found the pilot in Iran using some quantum magneto.
God knows that might be absolutely true. I did not see that.
Right. I mean, but it's also it seemed like there was quite a lot of marketing effort put into this secret that leaked. You know what I mean? So they want us to know about it.
I would tell that quantum. Those people think that it is. They think that one day you said this, and they said that you're probably reading things that are of different classes of technologies.
Sure.
And quantum computers there's immense advances. Might as well. Even if you don't believe in it, how about you be prepared for it?
Yeah, or just do 10 minutes of independent research on it, guys.
Yeah, just look into it.
So one last question. There's all these different platforms for quantum computing, right? There's photonic, neutral atoms, ionic, superconducting. What if you had to pick one? Now I know you don't know, nobody knows, right? But if you had to pick one that you thought was going to win, which one would you pick?
I truly do not know. I mean, I've got friends, and I represent an organization that has many, many members, and all of them are scattered. So even for the sake of the neutrality, I cannot name one. But I'm a photonics person myself, so I'm not saying that I'm not saying that. But
no, obviously I'm going to clip that out, and I'm going to hold you to it. And if it doesn't happen,
I find that more interesting, just because I understand the basis of it more.
No, I think I just like light. I think it's awesome, so I actually really like photonics as well. It feels like it's the easiest way to see the quantum phenomena is, the double slit experiment.
But the chandelier things are even more exciting and they're more beautiful.
It's a kaleidoscope. Well, it's been a pleasure, Dr. Zina. Thank you so much for coming on the show. I know you've got an event right after this, so let's get to that. But
Awesome. Thank you so much. It was so much fun.